Hi everyone. Let's talk about continuity and discontinuity in functions and what is a condition for any function to be continuous at a point in its domain. This is a three condition. You take it one by one. So fc is defined at c, any point or value of x in the domain of the function f of x. What does it mean defined? It means a real value. When you substitute by x equal to c, you should have a real value. The second one, the limit at x equal to c for f of x exists. What does it mean exists? It means, as the previous video, the right limit should equal to the left limit. Okay, so you know the value of the function at x equal to c, and you guarantee your limit exists if the value of the function at x equal to c is the same as the limit of the function at x equal when x tends to c or approach c. So in this case, you can guarantee your function is continuous at x equal to c. Now, we know this is a rational function. Okay, so we always, with the rational function, especially when your numerator and denominator are polynomials, we have a problem with the denominator. We don't like to have the denominator value as 0. So, for sure, without thinking, at x equal to 1, we have a problem. So, we should avoid x equal to 1, right? In the domain, right? Okay. Now, we have to check at x equal to 1, continuous or not continuous, right? If we graph this function, we have a line. How we get a line? Because this function, after we factorize the numerator, because we have a negative sign here, so we factorize the 3 into two numbers because 3 is a prime, so we have only 3 and 1 as a factorization. Because we have a negative sign here, we should have one negative and one positive, okay, for the factorization. Because we have in the middle positive, so the bigger one will be with the positive and the smaller one will be with the negative. Here x, here the other x. If you'd like to check, you can multiply them to check you have the same polynomials, okay? And here you have x minus 1. Now you can cancel out this one with this one, and you end up with x plus 3. So f of x is only x plus 3 when we avoid x equal to 1. This is why when you graph this one, we have it as a line. But as we said, we exclude x equal to 1. Okay? So to get the left limit, we come from the left and see the height. The height is almost 4. The right limit, we come from the right. So the height almost 4. So the right limit for f of x when x tends to 1 from the left equal to the limit when x tends to 1 from the right equal to 4. But we still missing the other condition, so the limit exists. So the limit exists, limit for f of x exists. We write exist like this one, and the value is 4. But we have a problem as the function equal to 1. The function of 1 is undefined. Okay? So we said f of x is not continuous at x equal to 1. So f of x, which originally is x squared plus 2x minus 3 over x minus 1, is not continuous at x equal to 1 because we're missing the value of f1 is not defined. Because if we plug in x equal to 1, we have the value of f1 is undefined as we sit here, because we're dividing by 0, which gives us undefined value. Now, if we have a function with such a graph, and we would like to check where the function is continuous or not continuous, and why. We have a problem at x equal to 1, so the left limit is 0, the right limit is 1. Okay, so the right limit when x tends to 1 from the right for f of x is equal the height here 1, and the left limit when x tends to 1 from the left for f of x is equal to 0. So yes, limit x tends to 1 for f of x does not exist. So we miss this condition. Now, the other point is x equal to 2. Okay, if we go from the left to 2 and from the right, we have the limit when x tends to 2 from the left for the function equal to the limit when x tends to 2 from the right for the same function equal to what? What is the height here? Is 1. So the function exists, but limit when x tends to 2 for f of x exists and equal to the same value here, 1, but this is not equal to the function at x equal to 2, which is what here? Is 2. So we're missing the condition. So f of x is not continuous at x equal to 2. Okay. Now, we can talk about this one. We have a problem as x equal to 1 and 2, and also 4, because the function at x equal to 4 is not equal to the limit, which is 1 here. Okay. Now, we check when discontinuity can be removable and when we cannot remove the discontinuity. Okay. As we said here, the left limit is not equal to the right limit. In this case, we cannot remove all this one. And we call it jump, because you jump from left and right to different place. But at x equal to 2, here, the left limit equal to the right limit equal to 1, but the value of the function is 2. So if you make the value of the function 1, you will satisfy the condition of the continuity. The right limit equal to the left limit, so the limit exists and equal to the value of the function. Also here, you have a problem with the value of the function, which is half roughly. So if you make the function, the value of the function is 1, so you remove the discontinuity. Okay. So as I said, At x equal to 1, we have a jump discontinuity, which we cannot fix. But in the other two, we can remove the discontinuity, so you call it removable discontinuity, by redefine the function at the value of the discontinuity to equal the limit of the function at this value. Now, all of these functions, transgeometric function or the inverse of transgeometric functions, the exponential function, the n-root function, all of these one are continuous for all x, okay, except the n-roots when n is odd and x should be greater than 0, right? And for the inverse sine and for the inverse cosine, they are continuous for the value of x between -1 and +1. Okay. Now, the function is a root function, right? So for the domain here is what? The domain is the value of the x making whatever under the root square should be greater than or equal to 0. So move this one to the other side. So when you have this one, so x between -2 and +2 equal, right? So your domain is -2 and 2, closed interval. So we know the domain. So the function is continuous in this domain, in this interval, right? Okay, because even if you graph it, you will have half circle with a radius 2 and center 0 and 0. Now, we know the step function, okay? The step function is equal to 1 for positive x or 0 and 0 for any negative value, right? It's also jump discontinuity because the left limit is 0, the right limit is 1. So this is the jump discontinuity at x equal to 0. Now, if we have this graph for different function, this is the linear function, okay? It's continuous because the left limit and right limit are equal to the function at x equal to 0. So this is it. But here the right limit equal to the left limit equal to 1, but the value at f of 0 is undefined. So f of 0 is undefined. This is removable or not removable? This is removable. If we define the function at x equal to 0 to be 1, we close this all and make the function continuous. Also here, the right limit equal to the left limit equal to 1, but the value of the function is 2. So if we redefine the function, we can remove the discontinuity. So instead of having f of 0 equal to 2, we make f of 0 equal to 1, right? So here this is continuous. We have no problem with this one. At any value of x, if we are considering 0, it's okay. This is discontinuous at x equal to 0. This also, but this one removable discontinuity. Here we have jump here, right? Because the right limit is not equal to the left limit. So this is what jump discontinuity, which we cannot remove. Okay. Let's go for these two functions. Okay, if we come from the left, the limit when x tends to 0 from the left for this function is infinity, and also the left limit when x tends to 0 from the right is also positive infinity. So the limit exists and equal to infinity. Okay, but is it continuous? Of course not. So f of x, which is equal 1 over x squared, is not continuous at x equal to infinity. Okay, and this one is could be removable. Yeah, could removable, but if the value of the function, if it is infinity, it is defined. This is question for you. Okay, go for the last one, y equal to sine 1 over x. We have a problem at x equal to 0. The angle is undefined, so we can know the value of the function. So this is the jump discontinuity. Okay. For this function, y equal to 1 over x, the left limit when x tends to 0 from the left for 1 over x is equal to negative infinity. But the right limit when x tends to 0 from the right side for 1 over x, we have it as infinity because you're going to infinity. They are not there. So the limit when x tends to 0 for 1 over x doesn't exist. Sorry. So once the right limit is not equal to the left limit, we call it, jump discontinuity. Okay. Now, for this function, the identity function y equal to x, because the same value of y is the same value as x, so we call it the identity function. We have no problem at any point x. Okay. So this is continuous for all x. Okay. This is a constant function which is a horizontal line, because we know when y equal to constant, we call it horizontal line. And the horizontal line has a slope equal to 0 because he has no slope with x. Okay, he's parallel. It is parallel to x, so the slope is 0. Yeah, the slope equal to 0. Okay, this is what we know. So it's also continuous for all x. Okay, any real value. Okay. Now, if we have two functions, both of them are continuous at a specific value, what about the addition and subtraction of these two functions and also the multiplication and division? As no surprise, The addition subtraction will be also continuous at x equal to a. The multiplication will be continuous at x equal to a, as well as the division of the two functions will be continuous. Under one condition, for sure the denominator should be 0. So when you divide it by the function, guarantee this function at this point is not 0. Otherwise, it will be undefined value. So if you have two functions and subtract them, adding them, multiplying them, dividing them, it will be the result will be continuous. And make sure with the division you divide it by non-zero value. Okay, now again, how we can do this one? At x equal to -1 and 4, we have a problem, because this one you can factorize it as we have done last time, because we have negative here, so we have one negative and one positive. 4 must be factorized at two numbers with sum equal to 3, one of them positive and a negative. So we can make it 4 and 1, but you should take the bigger one with the sign as a midterm, and the smaller one with the positive. So the big one, once you have negative here, you have two different signs, and take the bigger one of the factorization with the sign as a midterm, right? And here is x, here is x. So we have a problem at x equal to -1, and we have x equal to -4. So we shouldn't have x equal to this one or x equal to this one, right? Now let's go and do the graph for this function. So if we graph it, we have a problem at only x equal to 4, right? Minus 4, sorry. X equal to 4. Okay. We don't have a problem with x equal to -1. Do you know why? Okay, yes. Because when we factorize this one, we have the same factor, x plus 1, so it will be cancelled out. Catch it? Yes. Now, here is a function again. Show the following functions are continuous on their natural domain. For this one, we know the domain. The domain, how you get the domain for the root function? You take whatever under the root and make it greater than or equal to 0. Factorize this one. So you have x here, x here. 5 is a prime number, so it is 5 times 1. Because you have negative here, so I have one negative and one positive. But because of the midterm is negative, take the negative with the bigger one. So whether the function graphed is continuous or not, and if not, where does it fail? Yeah, we have a problem at x equal to 2 in this case. The left limit equal to the right limit equal to 1, but we have to define the value of the function at x equal to. So this one is not continuous. Why is not continuous? Because f of 2 is not defined. Okay. This one, at x equal to 2, the left limit equal to the right limit equal to 2. Okay. And the function is equal to 2. So it is continuous at x equal to 2. What about 3? No, it is not continuous at x equal to 3. Why? Because the function at x equal to 3 is not equal to the limit of the function when x tends to 3 or approach 3. Okay? But this is removable discontinuity here, so we can remove the discontinuity. This is removable discontinuity. Removable discontinuity. How to remove it? You just define the function at x equal to 3 to be similar to the value of the limit, which is 3. Okay, so if you define f at 3 to be equal to the limit, you can remove the discontinuity. For this function, no, this is continuous. We have no problem with this one. Okay, this is continuous. At x equal to -1 and at 1, sorry. It is exercise, is not continuous. Okay. Okay, I will leave this one for you as exercise and you can do it. Thank you.